Hi everyone, so very happy to be with you here today. Excellent. So my objective today is to bring you awareness and ideas on how you could develop smarter and more efficient embedded vision system using MIPI I3C. So today I will present you why and how, in fact, you can use MIPI I3C for building your next generation embedded vision systems. It's the wrong clicker. Okay. I had the wrong device. Yeah, excellent. So we have 4 agenda points today. I will start with a bit of context on embedded vision and the challenges behind it. Then I will explain you why MIPI I3C can be an excellent solution for embedded vision systems. We see then how we can use it to build even smarter embedded vision systems. And finally, some perspectives on what will come next. Starting with embedded vision, so why does embedded vision matter? Just to set the scene and give a bit of numbers. So the embedded vision market, we are talking about an aggregation, in fact, of different market segments. Because embedded vision systems are, in fact, systems made of a camera and a processing board, by opposition to traditional vision systems that need a PC. So it's a sort of autonomous system from a processing point of view. And in the embedded vision systems market, we are talking in the forthcoming years about 8 billion vision systems to be added in our day-to-day life, from smart glasses to wearables. In parallel, it's 200 million vision systems that will equip just the XR segment, whether it's smart glasses or complete VR headset. And to talk a bit about robotics, we have seen robots populating our houses, our factories, so we expect it to grow by 20% in the coming years. So the market is huge, potential is huge, but so are the challenges we need to overcome. So you can see displayed here a typical example of vision system with those smart glasses. The smart glasses, they have a huge potential. They can be used for live translation of text, for embedded world visitors that don't speak German. It's a very good tool. But also for surgeons, during operations, you can have the overlay of vital sign information. And for engineers, that we are, we can interact with 3D model. So the promises are great. So I'd like to propose you a survey. So based on the promises I just mentioned, and looking at this picture, I propose you to raise your hand if you would be interested in wearing those glasses. How many? Okay, about half of the audience. Okay, so it's mixed. Have you ever tried smart glasses? Yes? No? Okay. I would not wear those glasses, and I will tell you why. I did try smart glasses. They seemed much lighter than those ones, and to me it was already too heavy and too bulky. And this would be even worse here, I think. So I wouldn't wear them even for 1 hour, on my opinion. And these are, in fact, 2 of the main challenges for embedded vision systems. We need to make sure that they are small and light enough so that we can enable small systems that are ergonomic also. A third point is power consumption. You would not want to buy smart glasses that you must charge every hour. Finally, cost, because we are all potential customers and we need to make sure the price is not high enough so that we can democratize the technology. So 4 key points, to which we must add latency. For several market segments, not all of them I agree, but for the most promising one, we need also to pay attention to latency. When we talk about robots, such as the collaborative robots illustrated here, we need low latency to make sure that the robot will not harm the people around. For the mobile barcode scanners, we need to ensure low latency to scan the barcode in time. And finally, if we talk about drones, we need to make sure that the drone can land safely, so the low latency is also essential. By latency, in fact, we need to consider the full latency change. So it's about the latency in the sensor to detect a scene change and to capture it. We are talking about the latency on the host side to process the information, but finally also the latency in the interaction between the host and the sensor. And this is exactly where MIPI I3C comes into the picture. So we can now go to the heart of the presentation. Why using MIPI I3C? To give you just a bit of context, so the I3C was first published in 2016 with a brand new version released last month. The I3C, to make it simple, it's an improved version of the I2C. and to the 3 in I3C. Many new things that are brought by the I3C. If we focus on embedded vision, there are 4 major points that are very important for embedded vision. First of all, higher data rates. If we compare I2C, that is very known today, to the I3C, it's 10 times more data rate that we can achieve with the I3C, and this opened the door to new use cases. I2C was mostly used for control. With the I3C, we opened the door now to have data streaming, image streaming. Second point, lower power consumption. The way the data are sent has been optimized to lower the power consumption down, which is key for the embedded vision systems, as we have seen. A third point, enhanced flexibility in using different sensors. I will show you some example afterwards, but what is nice with the I3C protocol, on top of just sending simple data, we do have a lot of things specified related to smart features you can use for multiple sensor usage or event triggering. Finally, very important point, the backward compatibility with the I2C. If you have already designed using the I2C, with the backward compatibility, you can switch to the I3C. It is very important if we think about the main components to put in a vision systems, which are the sensor and the processor. There are a lot of microcontrollers today equipped with I2C, and there is more and more equipped with the I3C, and this is made possible by the backward compatibility. So with I3C, a first good point is that it opens the door to the use of microcontrollers in vision application. You got the example right before for those who are already there of the STM3226, but there are more and more. So I3C, higher data rate, lower power consumption, more features, and the use of microcontroller that is now possible for embedded vision. Yeah. So you may wonder, what does it mean in practice? I3C, if we compare it to the most standard interface. First of all, if we compare to I2C, I was mentioning that I2C is enough to do basic control, a little bit of communication, but it was way not enough for image streaming. With the I3C, 10 times higher data rate, we can now consider doing image streaming. I will give you some more numbers in the next slide. If we want to do a comparison, it's good to look also at the MIPI I3C over D-PHY, which is now very popular for imaging systems. The MIPI I3C was a very good improvement compared to the LVDS and SURDUS channels that were used in traditional vision system for the lower power. In fact, with the I3C, we can reach even lower power compared to the CSI2 over D-PHY. If you look on the microcontroller side, it's 100 times less power consumption just for the receiver. So power consumption will be lower, which is key for embedded vision, as we have seen. The number of wires also is significantly lower. If you have in mind, again, the example of the smart glasses, that we want to be as small as possible, the number of wires will be key also to ensure tiny systems. If you compare traditional MIPI I3C systems, the sensors does have 1 to 4 MIPI channels, and that means from 5 to 11 wires that one must connect between the multiple data lanes, a pair for each MIPI channels, plus the I2C, 2 lanes, plus the clock, 5 to 11 wires. With the I3C, you can completely optimize. It's just 2 wires that you need. So it's a perfect optimization compared to the MIPI I3C over D-PHY. Finally, I was talking about microcontroller. An interface that is pretty common today is the SPI. So how does MIPI I3C compare to the SPI? When it comes to absolute optimization, the power is still unbeatable. The number of wires also, 2 compared to 4. Finally, important point with the I3C, you have much more features that are enabled, and that will be very useful when you have several sensors to use, as we will see a bit later on. So I3C, in short, low power, very good optimization, good enough data rate, and many features that can help you with the embedded vision systems. So the MIPI I3C protocol, we saw it can be an ideal solution for embedded vision systems. We have now microcontrollers equipped with MIPI I3C, so the only thing we were missing is image sensors equipped with MIPI I3C. It's the case now with the VD55G1 sensor that we just released. This sensor here is teeny tiny, as small as a pen tip, so 2.7 by 2.1 millimeter, so very small. It won the Best of Sensors Award last year, and this is thanks to the many things we put into this sensor. First of all, teeny tiny size enabled by the world's smallest global shutter pixel, 2.16 micron. So you can have 800 by 700 resolution, even wider than VGA, fitting into the size of a pen tip. The sensor is also very low power, so typically for 30 frames per second, it will be 20 milliwatts. At 60 frames per second, 35 milliwatts. So very low power sensor. And that has the specificity of being dual interface. With this sensor, you can choose to output MIPI CSI, the classic way, but you can also choose to have the I3C used as an image streaming interface. So you can connect it to microcontroller equipped with MIPI I3C. To give you some numbers, I mentioned some data rate. What does it mean in practice? For typical resolution, you can see here the frame rate. What you can notice from this table, of course, we will not use the MIPI I3C to do slow motion or high-speed PCB inspection. That's not the point. But for most of the imaging application, mainstream one, if it's about reading the barcode on a coffee pod for a coffee machine, if it's about looking if there is no intruders around your vehicle, then the frame rate we can achieve with MIPI I3C is way enough to do simple application. You see that you can reach a few dozen frames per second. And knowing that you can do AI character recognition from a resolution of 128 by 128, typically, it's perfectly suited for those type of application. To show you a very simple example, a very basic one, in the example of a smart water meter reader, a typical architecture. So you have here a presentation of a board that exists, that is available on our booth, if you want to have a look afterwards. On this board, we put our VD55 G1 image sensor integrated into a tiny camera module, plus the STM32H5 microcontroller, all on the same tiny chip. So in practice, we'll have the sensor performing the image capture, downsizing the image to 300 by 300 resolution, outputting the data through I3C to be received by the microcontroller. Then we have two neural networks embedded into the microcontroller. A first one is performing the segmentation of the character into the image. And the second neural network is just performing the optical character recognition. What you get out of it is just the characters. So that's a very basic example of what you can do with I3C in terms of embedded vision systems. Simple example, but what can we do more? And how can we enable even smarter embedded vision systems? A first answer lies in the use of the many embedded features you can now find in image sensors. The world of image sensors have made a significant leap forward with the introduction of 3D stacking technology. 3D stacking technology, to make it simple, with traditional image sensor, you have this chip, one layer. The blue area is the pixel array, and basically around it you have data readout and processing, all on the same layer. With 3D stacking, and in the most advanced 3D stacking processes, as we implement at ST in our fab, we are able, in fact, to stack two chips, two layers, and to interconnect them. For the image sensors, it means that you can have a top layer allocated to pixel array and capturing light, and a bottom layer allocated to the data readout and processing. What you may not see from your eyes on this picture, but you have to believe me, it's the exact same surface, the pink one, between the left and the right drawing. So that's a very simple way to show you that with 3D stacking, not only can we have smaller chip, as you can see here, which is important for embedded vision, but we can also win extra space on the chip to put some more features. So this is now how we can put many and many smart features into the sensor. In the VD55 G1 sensor I was introducing just before, the teeny tiny one, we have all those features implemented thanks to this 3D stacking architecture. But there is only one I will focus on today, it's the auto-wakeup. What is auto-wakeup? Think about this very simple example of a conveyor belt. Imagine you have a camera on top of it, and what you want to do is whenever there is a parcel coming, you want to capture it to know what type of parcel or object it was, to look maybe at the size it has, but also to look at the barcode or QR code to track the parcel into the warehouse. With a traditional vision system, you will keep capturing, streaming, and analyzing images all the time. But what happened here? Well, maybe there is no parcel or there is nothing in the field of view. So why should you capture images and analyze it? The principle of the auto-wake-up is to say that when there is nothing particular happening in the field of view of the camera, then you don't need to do anything specific, and you can make it run at very low power. Whenever there is something happening, then we can wake up the system, capture the full resolution image to look at the parcel, the size, and read the barcode. With the auto-wake-up, you have 2 degrees of freedom, principle 1. First one is the trigger for what is a significant enough change to activate the system. So you can trigger from what level we can wake up the system. A second level of freedom is a region of interest that you can select. And the main interest is region of non-interest. If we think about this example here, you can, for instance, assume that whatever happens here is interesting because it's your parcel. But if there is something moving or happening left or right, it's not a parcel, it's just an operator that is passing by, so you don't need to wake up the system. So that's basically, from a top-level view, how auto-wake-up works. From a sensor system point of view, how does it work in practice? So your host SoC will go into idle mode, so consuming very low power. It won't do anything. The sensor itself, when in auto-wake-up mode, basically will perform on its own a scene analysis, so it will capture images, analyze them, just a sensor. If there is an event significant enough happening and in the region of interest you define, then the sensor will send a trigger signal to the host asking for the wake-up and then for the full streaming. The main point, if you think about power optimization, the sensor, instead of the 20 to 35 milliwatts I was mentioning before, will consume only 1 to 1.5 milliwatts, so you win in power consumption on the sensor side. On the SoC side, when nothing happens, maybe 90% of the time, the SoC is not at full power consumption, but only in idle mode. So you can optimize on the SoC side and on the sensor side. An example of implementation, what type of smart systems you could do with this I3C. Think about a doorbell camera that you would put in front of your house. You want it to be always on, because a delivery guy can come and put a parcel in front of your house, but it can be also an intruders that want to break into your house or to steal your parcel. This is happening sometimes. So you would like your camera, whenever something happens, to be waken up. And it's battery powered, so you need to optimize the power. What you could do, a very simple example. Think about the STM32N6 that was just introduced before has a specificity to have both the CSI2 and the I3C interface. So a typical example, you could state that you want to have the VD55G1 sensor with its auto-wake-up capability connected to the I3C and a high-resolution color camera with the CSI2. So with this system, you can have a low size, low power microcontrollers and 2 cameras connected to it. What will happen in practice? You're using the auto-wake-up, so the sensor is in sleepy mode. Your high-resolution sensor and the microcontroller are just waiting for something to happen. Suddenly, there is something happening in front of your door. So the sensor that is performing its analysis routine will send a trigger through I3C to the microcontroller. The microcontroller will wake up and ask the VD55G1 sensor to send an image, a streaming. It's low resolution, so VGA type of images that will be sent again through I3C to the microcontroller. The microcontroller from that point can perform an analysis on the image, again VGA type of images, so we are not talking about full resolution 5 to 8 megapixel, so it's a light AI algorithm that you can perform here. And then there are 2 scenarios. The microcontrollers analyze, segment, classify, and in fact it's not a person, it's a dog, so it's your dog that is just in front of your house. In that case, the microcontroller will tell the VD55G1 to turn back to sleepy mode, and you haven't consumed much. If it turns out it's a person, then it will ask the high-resolution sensor instead to start streaming. We will get a high-resolution color image streaming through CSI on the microcontroller. So this is typically the case in real life when you will have a notification of your cell phone saying that you should have a look, something is happening in front of your house. So this is a very typical example of how we can enable a smart, always-on vision system using the I3C. What's next? So future perspectives, what can we do more? In the example I gave before, you got either the image streaming through the I3C or the image streaming through the CSI. Well, you could do both in parallel. An example, typical example, would be road mapping for home robots. We see more and more home robots coming into our houses. So very simple one can just do the cleaning, but you have more and more advanced model that can avoid obstacles, not get tangled into cables. And if you looked at the latest releases at the CES, the robots, they can now climb little steps. So they do it by having both an image information plus a depth information. And for the most advanced one, as announced at the CES, they can also sort objects. So imagine your children, sometimes they left a bit of mess in your home. Well, the robot can clean it up for you and for your children. I'm not sure it's a good news, but it's a possibility you have now. And this is done by combining 3D information, distance, shape of the object, but also the 2D color information identifying the type of object. So for typical home robots, we do need a color camera information, but we need also a depth information. You could do it at low power, low size, and low cost, still with this same STM32N6 microcontroller, the high-resolution color camera on a CSI, combined with a multi-zone DTOF sensor. So the principle of the DTOF, you measure the travel of light, and the longer it takes, the further away it is. With multi-zone, we're able to do room mapping, so we could have the 3D information, the color information, and you could put all of that in a microcontroller. So this is what is enabled now with the I3C. One step forward, in all the example I gave you, there was only one sensor connected to the I3C, while the I3C enables you to put different sensor modalities on the same I3C bus. So in practice, it will just be a matter of the refresh rate you need for the different sensor modalities. If you think about a robotic arm, you could have an image sensor, an accelerometer combined with a DTOF sensor. Then it's just a matter of, yes, the refresh rate you need on the different sensor modalities to make sure you can pick up the object in time and avoid people. And this is very nice with the I3C because they did implement a lot of features very useful for multi-sensor usage, such as the inbound interrupts. So in the communication protocol, you don't need a GPIO, an additional GPIO. You can notify of an event and pass the master control to another sensor. The I3C does support also dynamic addressing. So if you have ever tried to put different sensors, sometimes one of the issues is you can have conflict of addresses. This is solved with the I3C, for example. We have also the hot join capability with the I3C. So if you have one of the sensors that is suddenly broken and doesn't work, then you can add an additional one and do not interrupt the system if it's a critical application. So all of this is made possible with the I3C. So we have nice use cases, sensors, microcontrollers. Now to enable people to use MIPI I3C, what do we miss more? How to enable its democratization in the coming years? A first point is about product availability. I was mentioning the very first image sensor release with I3C. More and more will come and must come. On the processor side, we need also more solutions to be equipped with I3C for its democratization, and we need increased collaboration between the different components manufacturers. Second point will be development tools. If you are very interested in the example I gave, what we need next is development tools, so turnkey kits, drivers, trainings, and tutorials to make sure people can easily adopt. And finally, bringing some activity to the community, use case studies, such as the one I presented, and Linux environment to benefit from the community. So as a takeaway in short, a first point, so embedded vision, we saw very important market, but huge challenges, to which MIPI I3C can be an excellent solution. With the higher data rates, it's now available and perfectly suited for image streaming. It's backward compatible with I2C, and it comes with a lot of features. So you can use it to design ultra-low power camera, and combined with sensors having auto-wakeup capabilities, it can enable always-on low-power camera system, and even sensor fusion at the edge. And its adoption will be facilitated by the point I mentioned before, so more product development tool and use cases. If you were interested in the topics I mentioned, I do invite you to stop by our booth. It's Hall 4A, stand 148, so it's at the complete bottom of the Hall 4A. There you will be able to witness live demos of what I presented using the I3C and meet with our experts. If you have interest in some of the products I presented today, you can flash these QR codes. The left one will bring you to the ST BrightSense family of CMOS image sensor we released. It includes the VD55G1 sensor I was mentioning, teeny tiny low power with auto-wakeup. The right QR code will bring you to the STM32N6, which is one of our latest microcontroller equipped with I3C, which on top includes an NPU for artificial intelligence. But we do have other microcontrollers equipped with it. And finally, I do invite you to subscribe to the newsletter if you're interested in MIPI I3C, image sensors, or microcontroller. Staying on the topic of I3C, we will have some exciting news from this summer, some fresh news on the I3C. So if you want to be the first informed, I do invite you to subscribe to the newsletter. And that will be all for me. So I guess we can switch to the Q&A session. Has anyone question on this topic? No, we are approaching lunch break, so okay. So thank you very much for attending, and don't hesitate to stop by if you're interested. Okay, thank you, guys.